Hello everyone, my name is Simon and of course I like to solve math problems for you all to better understand math. Today we will be covering Algebra 1, the topic on the types of numbers. It is very important to know how to classify each number since we deal with numbers daily. It can be very useful when solving equations and all sorts of applications that deals with numbers. Um, so in this picture below, it's by the BYJU. You can see the different types of numbers that we have, such as the real numbers, rational numbers, irrational numbers, integers, whole numbers, natural numbers, and complex numbers. Uh, we will only be focusing on everything except complex numbers since this is Algebra 1 and complex numbers usually shows up in Algebra 2. Let's begin. Alright, so first we have the natural numbers, aka or the counting numbers, which are the set of all positive numbers from 1 to infinity. And a quick history behind the concept of natural numbers assumably began in the prehistoric times when we had tally marks to keep track of quantities such as coins, animals, days, and so on. Then comes the Egyptians and Babylonians, where the Babylonians established a place value system starting at the numeral 1 to the numeral 10. The Egyptians included numbers up to the powers of 10 to 1 million. Then we have the Greeks, particularly the Pythagoreans around the 6th century BCE, were among the first to study the numbers formally. They viewed natural numbers as fundamental to understanding the universe. Um, and we have these significant images of the number system used back then. And it's crazy to see how much things have changed and evolved over time. And the natural numbers are most commonly denoted by this capital N right here, this symbol. And an example of the natural numbers are, of course, your regular 1, 2, 3, 4, 5, and so on, all the way to infinity. Um, and you can also just count the number of items in this basket right here. And of course, the number of students in the classroom, right? Next, we have the whole numbers, which are the set of all natural numbers, including 0 and 0. It's 0 was invented independently by the Babylonians, the Mayans, and Indians, although some researchers say that the Indian number system was influenced by the Babylonians. They are commonly denoted by the capital W symbol right here. And an easy example is 0, 1, 2, 3, 4, and 5, and so on. Next, we have the integers, which are the set of all positive and negative numbers, including 0. So they contain all natural numbers from 1 to infinity. They also contain the whole numbers in like 0, and they have all the negative numbers, as you can see in the number line below right here. The concept of the negative numbers was not embraced wholeheartedly by mathematicians until somewhere around the 17th century, according to David Arnold from St. Martin's University. Some people would say that the integer was first introduced in the year of 1863 when I think it's
Abermount Holtz.
Abramoff Holtz. I apologize if I mispronounced that name. Um, who was busy with his bunnies and elephants experiments. He kept account of the amount of bunnies in the cage, and after 6 months he found the amount of bunnies increased. Then he thought of inventing a number system of adding and multiplication. He spent 15 years developing this number system. And the integers are denoted by this capital Z right here, which stands for, I believe, Zahlen, I believe, which is a German word for integers or numbers. The symbol first occurred in an algebra written by the collective Nicholas Bourbaki. Again, I apologize if I mispronounced the name. Dating to 1947. And here we have all the negative numbers on the left side, and we have the 0, and on the right we have the natural numbers, 1, 2, 3, and so on. Next, we have the rational numbers, which are the set of all numbers that can be written by dividing one integer by another. Note that you cannot divide a number by 0, and you can find the reason online. I think Khan Academy explains it well. I think an example that shows that we can't divide a number by 0 is consider 1 divided by 0, right? So that means a number q, let's say q, multiplies or times 0 is 1. Can you find a number q that is an integer that proves this? And it turns out that no, it's quite impossible. You can't find a number q that is an integer that multiplies by 0 that gives you 1. So rational numbers are denoted by the capital Q, which in 1895, I believe a person named Giuseppe Piano, again, these names are quite hard to pronounce, came up with this, which was the Q came from quotiente, which is an Italian word for quotient, and it first appeared in Bourbaki's algebra. So an example is of a rational number is 1 over 3 or -1 over -3, right? Because you're dividing 1 by an integer, 1 is an integer, and you're dividing it by another integer. Another one is 1, because you're dividing 1 by 1, so that's just 1. That's a rational number. -1/2, again, that's it's a ratio of two integers. 0.3, which is also written as 1 over 3, so that's a rational number. 0.0, that's actually a 0.3 repeating. There's supposed to be a bar up top. It's kind of blurry, so that's also a rational number. We have 0 over 1, and that's 0, so that's a rational number. So you can divide 0 by an integer, which is 1. We also have another rational number, 25 divided by 1, which is 25. And we have 3.27, which you can rewrite that as 327 over 100, which is a rational number. And I believe this is the last one, is -5 over 1. Again, it's -5, so that's a rational number. Next, we have irrational numbers, which are the set of all numbers that are not rational numbers. They have decimal expansions that neither terminate nor repeat. Hippasus, I believe, of Metapontum was a Greek mathematician and a member of the Pythagorean school, believed to have lived in the 5th century BCE. He is most famously associated with the discovery of irrational numbers, particularly the irrationality of the square root of 2. The Pythagorean school, founded by Pythagoras, was a philosophical and religious community that believed in the profound significance of numbers in the understanding the universe. They held that all quantities could be expressed as ratios of whole numbers, rational numbers, and this belief was central to their cosmology. They are often denoted by P, the capital P, but I usually use I just for simplicity, and I would represent the irrational numbers. I don't know where would the P come from, but some people use the capital P. So an example of an irrational number is square root of 2, where we have this long number that keeps going and it does not repeat itself, and it does not stop. So it continues to keep going, and so that you cannot represent this as a rational number. And another example is pi, right? 3.14, and it keeps going, right? There's no repeating numbers. It does not stop, so therefore it is a irrational number. Lastly, we have the real numbers, which this one's a fun topic. It's a fun type of numbers to talk about, especially in the near future when you take more advanced upper division math courses, such as in real analysis, right? They are the set of all numbers on a number line. They include all rational and irrational numbers. They have no gaps in the number line, which again, that's a topic that we'll discuss in real analysis in the near future. They are denoted by this capital R. An example of real numbers is 10, right? 10 is a rational number, right? 10 is an integer, a whole number, and a natural number. So it's a real number. Pi is an irrational number, which therefore is a real number. Negative 25, that is a rational number, an integer, right? And therefore it's a real number. 1/2, that is a rational number and an integer, right? Square root of 6, that is a irrational number, therefore it's a real number. So now it is your turn to try these questions, these problems out by classifying each number in as many categories as possible. So tell me if this is an integer, a natural number, and so on and so forth, right? So I'll give you, you can just pause this and complete this, and we'll check our answers. All right, so now it's time to check our answers. So for the first one, 100, that is a natural number, right? Because it's from 1 to infinity, right? So 100 is in between that. It is also a whole number, because the whole number contains the natural numbers. It is an integer as well. The integer contains the whole numbers and the natural numbers. It is also a rational number, because 100, you can express that as 100 over 1, or the 100 divided by 1, which is 100, and that is contained in the rational number. And therefore, if it's a rational number, it's also a real number. Next, we have 7 over 6. That is a rational number, right? Because you're dividing 7 by an integer. 7 is an integer divided by another integer, 6. So it is a rational number, therefore it is also a real number. And for the third one, 9.2, and this number continues to keep going. It does not repeat itself, nor does it stop, right? So it keeps going, right? So it's an irrational number, therefore it's also a real number. Number 4, we have negative 360. This is an integer, right? Because it contains all the negative numbers. It is also a rational number because you can express negative 360 divided by 1, which is negative 360. So it's a rational number. Therefore, it is also a real number. Square root of 36, that is also 6, right? So 6 is a natural number. It is also a whole number, an integer, a rational number, and therefore real number. We have 5.136, and this 6 is supposed to be repeating. There's supposed to be a bar up here. So since it's repeating, it's a rational number, and therefore it's a real number. Square root of 7, you cannot break this down even further to make it a rational number nor an integer. So it's an irrational number, and therefore it's a real number. And 0, again, we saw this in the previous slide. 0 is a whole number, therefore it's an integer. 0 divided by 1 is 0, so it's an integer. It's also, or sorry, that's a rational. I was talking about rational right there. It's also a real number. Negative 4 divided by 2, that is also 2, right? And negative 2 is an integer, right? The integer contains the negative numbers. It is also a rational number. Because if this is negative 4 over 2, that's negative 2. You can think of that as negative 2 over 1. Or I guess looking at this, you can tell this is a rational number. Because negative 4 divided by an integer 2. Therefore, since it's rational, it is a real number. And lastly, 10.2, you can rewrite this as a fraction, right? 102, I believe, divided by 10, I think, which is a rational number, and therefore it's a real number. So let me know how you did, and that is all for the topic of the types of numbers. I hope that this makes you guys, I hope you guys understand it better, and yeah, let me know what how I can improve, and yeah,